Hello everyone, and welcome to today's live broadcast, Applications of Micro-CT Technology in Endodontics, presented by Dr. Marco Versiani, dental researcher at the University of Sao Paulo, Brazil. I am Kiela Pere, Market Product Manager with Bruker, and I'll be your moderator for today's event. Today's educational web seminar is brought to you by LabRoots and sponsored by Bruker. Bruker enables scientists to make breakthrough discoveries and develop new applications that improve the quality of human life. Bruker's high-performance scientific instruments and high-value analytical and diagnostic solutions enable scientists to explore life and materials at molecular, cellular, and microscopic levels. For more information, please visit www.bruker.com. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting a question if you like, at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click on the Send button. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Answer a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process to obtain your credits. Lastly, at the end of the presentation, you will receive a poll survey, which we kindly ask you to complete. Your answers and suggestions will help us improve our webinar program and is greatly appreciated. Now I would like to introduce our presenter, Dr. Marco Versiani. Dr. Versiani is an invited professor and researcher at the University of Sao Paulo in Brazil. He's a certified specialist in endodontics, didactics, and bioethics, and has authored over 80 peer-reviewed papers in endodontics. Dr. Versiani has lectured worldwide, focusing on his main research interest in root canal anatomy and endodontic procedures, and it's thus a pleasure to have him here today. For a complete biography on Dr. Versiani, please visit the Biography tab at the top of your screen. Marco, over to you.
Hello, I'm Dr. Marco Versiani from Brazil. Today, I'll talk about the use of micro-CT in endodontic research. Endodontics is a specialty of dentistry concerned with the morphology, physiology, and pathology of the human dental pulp and periradicular tissues. To understand how micro-CT can be used to improve knowledge regarding the endodontic treatment procedures, it is important to know basic concepts about the anatomy of teeth. A tooth is made of a number of highly specialized tissues. The enamel is the hard outer covering visible in the mouth. Below this is dentin, a less hard and porous material that makes up the majority of the tooth. In the central part of the tooth, there is a space called the root canal, which contains the pulp tissue. Dental pulp is a non-mineralized oral tissue composed of soft connective tissue, vascular, lymphatic, and nervous elements, which extends from the pulp chamber, an area within the crown of the tooth, to the tip of the root, where it connects to the tissues around the root by the apical foramen. Teeth can be damaged by dental decay, fractures, and other reasons. This exposes the pulp to bacteria from saliva that may irritate it. Unless treated, the problem may increase and symptoms such as pain and swelling can occur. Eventually, the pulp space becomes completely infected with bacteria and the inflammatory response occurs, resulting in damage to the bone around the root, often appearing as a dark shadow on a dental radiography. Once this problem occurs, there are only two ways to solve it: either extract the tooth or carry out a procedure called root canal treatment. Root canal treatment can often be performed in 1, 2, or more visits and involves several steps. In the first step, an access cavity preparation is made to reach the pulp space and allow the location of the canals within the root. Once access has been gained to the pulp space and root canals have been located, the canals must be enlarged using a variety of instruments and techniques. The prepared canals are then irrigated with a variety of cleaning solutions. The irrigation process removes residual infected pulp tissue debris from the preparation of the canals and also bacteria. After shaping and cleaning the canal space, it must be filled with a proper material. A well-filled canal can prevent bacteria from infecting the tooth again. Once the treatment has been completed, and following a period of healing, the tissues around the root return to normal, and radiographs will show the resolution of any shadow, which means a bone lesion, around the roots. The invention of X-ray computed tomography provided a significant step forward in diagnostic medicine. CT produces a two-dimensional map of X-ray absorption into a two-dimensional slice of the object. This is achieved by taking a series of X-ray projections through the slice in different angles around an axis perpendicular to the slice. From this set of projections, the X-ray absorption map is computed. By taking a number of slices, a three-dimensional map can be produced. In 1990, Tachibana and Matsumoto in Japan were the first authors to suggest and evaluate the feasibility of CT imaging in endodontics. Because of high costs, inadequate software, and low spatial resolution, they concluded that CT had only limited usefulness in endodontics as the produced images were not accurate. A decade after the CT scanner was developed, Elliott and Dover developed the first high-resolution X-ray microcomputed tomographic device, the so-called micro-CT. However, application of micro-CT technology to endodontic research was recognized only after 13 years and described in a paper entitled Microcomputed Tomography, an Advanced System for Detailed Endodontic Research. In this article, authors evaluated the reliability of using micro-CT in the reconstruction of the external and internal anatomy of 4 maxillary first molars, assessing the morphological changes in the root canal after instrumentation and obturation, using an isotropic resolution of 127 micrometers. The authors concluded that micro-CT had potential as an advanced system for dental research. With further developments in micro-CT scanners, improvements in the speed of data collection, resolution, and image quality yielded greater accuracy compared with the first studies using computational methods, with voxel sizes decreasing to less than 40 micrometers. Micro-CT could now offer the possibility of learning tooth morphology by an interactive study of surface-rendered images and slices, and contribute to the development of virtual reality techniques for endodontic teaching. The first attempt to use micro-CT for a quantitative analysis of root canal anatomy was done in 1999. Authors correlated the shape of the root canals to the corresponding roots of 5 maxillary molars, scanned at a resolution of 33 micrometers. In the following year, Peter and colleagues studied the potential of micro-CT for detailing the root canal geometry of 12 maxillary molars regarding some morphological parameters including volume, surface area, diameter, and structure model index. Nowadays, this non-invasive, non-destructive, high-resolution technology is considered the most important and accurate research tool for the study of root canal anatomy. The anatomy of the root canal system is often complex, and from a clinical point of view, it is important for the clinician to be aware of this variability in order to implement an appropriate treatment plan and increase the success rate of endodontic procedures. Because of the non-destructive nature of micro-CT, this technology can be used for a precise and accurate characterization of the root and root canal anatomy. According to a recent comprehensive review on root canal morphology using micro-CT, a total of 37 root canal configuration types have been described, which probably include the most common anatomical configuration that can be observed in a single root. Qualitative 3D analysis can also be applied to evaluate the presence and location of older anatomical landmarks such as isthmuses, accessory canals, and apical ramifications. In the literature, Micro-CT studies on root canal anatomy evaluated anatomical variations present in specific groups of teeth, including the second canal in the mesial buccal root of maxillary first molars, three-rooted mandibular premolars, and molars. The digital images acquired by micro-CT are a geometric representation of the internal and external morphology of teeth. Therefore, a morphometric characterization of the root canal system can be performed through geometric concepts and morphological operations applied to the binarized images. In the first research studies on root canal anatomy using conventional methods, quantitative morphological data were obtained from measuring 2D parameters acquired from a few cross-sections of the root, including area, perimeter, diameter, and aspect ratio. In the past, images of the root canals were recorded together with a scale that allowed for further calibration of dedicated software. The operator was responsible for carefully tracing the contour of the structure to be measured by clicking and releasing the computer mouse button until the results were displayed. Therefore, outcomes of studies using sectioning roots were highly influenced by the operator. Using micro-CT technology, 2D parameters can be accurately measured and plotted on graphs in hundreds of slices at once. This is one of the greatest advantages of micro-CT technology over the conventional methods to study the morphology of the root canal system. In the past, the canal shape in sectioned roots was qualitatively classified as round, flat, oval, or irregular shaped. Despite its applicability, a qualitative evaluation is always subjective and may lead to inaccurate comparisons among studies performed in different research centers. Micro-CT has opened new possibilities for describing the cross-sectional appearance of the root canal by means of two morphometric parameters, roundness and form factor. Roundness of a discrete 2D object is defined by this formula, where A is the area and Dmax is the major diameter of the root canal. The value of roundness ranges from 0 to 1, with 1 signifying a circle. Form factor can be calculated by this equation, where A and PM are the root canal area and perimeter, respectively. Elongation of individual objects results in small values of form factor. Evaluation of root canal shape using these parameters in single-rooted canines have demonstrated different cross-sectional forms throughout the root canal in the same specimen. Description of 3D geometry of the root canals using conventional sectioning methods can only be estimated, but never acquired precisely. Therefore, this is one of the best advantages of using non-destructive methods such as micro-CT in the study of the internal anatomy of teeth. 3D analysis of the root canal using micro-CT algorithms allows for the calculation of volume and surface area. Volume is defined as the volume of binarized root canal within the volume of interest, while surface area is the total area that the surface of the canal occupies within the volume of interest. The clinical significance of such parameters has been emphasized by studies demonstrating that variations in canal geometry before preparation procedures have a greater effect on the changes that occur on the root canal system than that of the preparation techniques. Another important 3D parameter of root canals that can be measured using micro-CT is the Structure Model Index, or SMI. SMI is impossible to achieve using conventional methods such as radiographies or root sectioning. This parameter reflects the geometric 3D shape of the root canal and has been used in comparative studies of different groups of teeth. The similarities in SMI values among teeth must be taken into consideration during sample selection in studies on root canal preparation, as it might compromise the final outcome. Recently, Salmon and I are close to validate a new parameter to describe the 3D geometry of the root canals, named IROD index. Results from this research will be published soon. In the last 7 years, our group published several papers in which the previously mentioned 2D and 3D parameters acquired using SkyScan 1174 and CTN software were used to describe the canal morphology of different types of teeth. The endodontic access cavity is considered the foremost step in root canal treatment. It is defined as the opening prepared in a tooth to gain entrance to the root canal system. A proper access cavity is crucial for effective locating, negotiating, debriding, disinfecting, and filling the root canal system. Traditional access preparation are geometrically pre-designed shapes defined by the morphology of the pulp chamber of each tooth. The roof of the pulp chamber must be completely removed in order to locate and provide access to the root canal orifices. However, conventional preparations may remove a large amount of dentin, weakening the dental structure and reducing its resistance to fracture. It has been hypothesized that modification of the original access geometry plays a crucial role in the biomechanical responses of tooth structures to functional forces, since the remaining dentin can serve as a foundation for the restorative procedures that follow endodontic therapy. In this way, new designs for endodontic access cavities called conservative or contracted cavities have been advocated in order to minimize tooth structure removal. Contracted endodontic cavities are considered to be an alternative to traditional endodontic cavities in maintaining the mechanical stability and subsequently the long-term survival and function of endodontically treated teeth. Within this background, micro-CT imaging has been used to measure the volume of corneal enamel and dentin removed by different access preparations in an attempt to correlate those values with results acquired from fracture testing. One study showed that, with the enlargement of access preparation, the stress on the pericervical dentin increased dramatically and may contribute as a potential cause of root fracture. In another study, micro-CT was used to evaluate the relationship between some anatomical landmarks on the root canal in order to apply them in the design of different access cavity outlines in mandibular molars. Authors concluded that the outline design of the access cavity had a significant impact on root canal preparation. A remarkable advance in endodontics in the last century was the development of mechanical preparation using nickel titanium instruments. Manufacturers have experimented with different alloy type, tip, taper, cross-sectional configurations, rotation modes, and heat treatment during manufacturing in order to optimize instruments' properties. Indeed, more than 150 brands of nickel titanium instruments are currently available. With so many systems on the market, clinicians required an impartial evaluation of these instruments in order to select the most appropriate for clinical use. Over the years, several methodologies have been used to evaluate root canal preparation with these instruments. Advances in non-invasive micro-CT technology have brought new perspectives on the evaluation of mechanical preparation in endodontics, as it allows to co-register color-coded 3D models of the root canals before and after preparation with high accuracy. In this image, for example, unprepared and prepared canals are represented by green and red colors respectively. Unprepared and prepared matched canals can also be quantitatively compared regarding the percentage frequency variations of 2D and 3D parameters by subtracting values obtained for treated canals with those obtained for untreated counterparts. Evaluation of unprepared canal surface areas is important because these areas may harbor bacteria biofilm that may contribute to persistent infection. Using micro-CT, measurements of untouched root canal surface areas after root canal preparation can be obtained by calculating the number of static voxels, which means voxels present in the same position of the canal surface before and after instrumentation, expressed as a percentage of the total number of voxels present on the canal surface. As higher the percentage of untouched walls, as worse can be considered the root canal preparation. Canal transportation and dentin thickness are other important parameters to evaluate. If a root canal enlargement is followed by unnecessary dentin removal, it may compromise the tooth structure, leading to root fracture. Using micro-CT, canal transportation can be achieved by connecting the center of gravity of the root canal in each cross-section through the length of the entire root with a fitted line from the co-registered datasets before and after preparation using centroid values. Then, mean transportation in millimeters can be calculated by comparing the distance between the centers of gravity at each level of the root canal. Dentin wall thickness can be acquired by the measurement of the width of dentin toward the external root surface, perpendicular to a line that connects the center of gravity of the root canals after superimpositions of the datasets before and after canal preparation. Color-coded 3D models of dentin thickness can also be created for qualitative evaluation of using color-coded 3D models for structure thickness in CityVox software. In recent years, the occurrence of root fracture has become a major concern in endodontics. Root fracture is currently considered as the third leading cause of tooth loss that can affect either sound of endodontically treated teeth. In 2009, two studies using a conventional sectioning method associated root crack formation with canal preparation procedures. Since then, the phenomenon of microcrack has gained importance in endodontic research, and the number of publications in high-impact peer-reviewed journals correlating root canal preparation to crack formation has increased. Laboratory-based studies concluded that large tapered instruments can remove substantial amounts of dentin during root canal preparation, creating lateral forces that induce strain on the canal wall and cause root cracks from which tooth fractures can develop. In disagreement with previous studies using conventional sectioning methods, our group used micro-CT to demonstrate the lack of a causal relationship between the development of root fractures and canal preparation in extracted teeth. More recently, we have improved the reliability of micro-CT to evaluate root crack formation using a fresh cadaver model. Using this method, we have proved that preparation procedure itself cannot cause dentinal cracks. In 2011, it was demonstrated the feasibility of non-destructive micro-CT technology to identify and quantify the accumulation of dentinal debris in the root canal space after preparation, while preserving sample integrity. The disinfecting effects of chemomechanical preparation may be additionally hampered in the presence of complex anatomy, which cannot be properly accessed by conventional techniques. These areas may be packed with dentinal debris generated by the mechanical preparation. Accumulation of debris is considered an undesirable side effect of mechanical procedures, and it is clinically relevant because it could easily harbor bacterial content away from the disinfection procedures during root canal treatment. Quantification of hard debris can be performed by calculating the difference between the non-prepared and prepared root canal space using post-processing procedures. The sequence of acquired imaging can be further used to identify the debris by means of morphological operations. The presence of material with a density similar to dentin in regions previously occupied by air in the non-prepared root canal space is considered debris and can be quantified by the intersection between images before and after canal instrumentation. The total volume of hard tissue debris can also be calculated and expressed as the percentage of the total canal volume after preparation. Color-coded models of the root canal and debris can also be made to enable a qualitative comparison of the matched root canals before and after experimental procedures. Together with mechanical preparation, flushing irrigant solution throughout the canal space also acts mechanically and chemically on debris and bacteria colonizing the canal system. Efficient irrigation protocols are required to provide fluid penetrability to such an extent as to accomplish microcirculation flow throughout the intricate root canal anatomy and to counterbalance the debridement quality obtained by the mechanical enlargement of the root canal space. In laboratory-based studies, several experimental models have been used to understand the intracanal effect of irrigants by different irrigation protocols, including artificially created grooves, histological cross-sections, computational fluid dynamics, and in vivo use of dense solutions. These methodologies, however, are unable to measure quantitatively some factors, including the volume of the solution or the root canal areas effectively touched by the irrigant. Additionally, the destructive approach of these methods is a major drawback, since the preoperative condition of the root canal is unknown. Micro-CT technology can overcome limitations displayed by conventional methods for the study of root canal irrigation, as it can provide 3D quantitative volumetric and 2D mapping of the irrigant within the root canal space. Using micro-CT, the volume of irrigant can be also correlated to the full canal volume and the existence of anatomical irregularities of debris that may prevent its spreadability. The volume of irrigant-free areas can also be calculated and correlated, for example, to the irrigant delivery method, fluid activation system, irrigation needle penetration and design, root canal configuration, amount of hard tissue debris, or shaping protocols. Data can be further subjected to inferential statistical models to access the relevance of different irrigation protocols following well-known parameters. Root canal obturation is defined as a procedure in which any material or combination of materials is placed inside the canal after it has been completed, cleaned, shaped, and disinfected, aiming to avoid any sort of communication or exchange between the root canal and surrounding tissues. Conventional root fillings consist of a core material, usually gutta percha, which should be closely adapted to the root canal wall, and a sealer that seals the interface between the core and the dentin placed into the canal space employing different techniques. Cold lateral compaction of gutta percha is undoubtedly the most used and tough root canal filling technique worldwide. The basic protocol comprises the lateral compaction of accessory cones undertaken by systematically penetrating spreaders sideways of the main gutta percha cone. The core idea is to maximize the volume of gutta percha inside the canal while reducing the layer of the sealer. Another technique to obturate root canals is warm vertical compaction. It involves the use of successive heated pluggers and gradually pushing down compaction to form waves of softened gutta percha, aiming to obtain an homogeneous and dimensionally stable mass of filling material. As gutta percha is heated, it becomes more plastic and therefore adapts to the irregularities of the root canal walls. Since the development of the warm compaction techniques, there has been debate regarding their superiority in comparison to cold lateral compaction. Although studies have demonstrated that no filling techniques produces a void-free canal filling, warm vertical compaction is associated with a lower percentage volume of void, while cold compaction techniques suffer from unpredictable distribution of the sealer and voids within the root canal space. In the past, the quality of root canal obturation was investigated using several laboratory-based techniques. In many studies, the percentage of gutta percha filled area was used as a surrogate measure of the quality of the root filling. However, most of these methods allows only a partial evaluation of root fillings, and some may create irreversible damage to the specimens. Besides, inaccuracies are expected because some filling materials might be lost during sample preparation. Although radiography does not cause any damage to the specimens and provides useful information, it has limited accuracy since it's based on two-dimensional visualization of a three-dimensional object. Therefore, an ideal experimental model should allow for the preservation of sample integrity to avoid irreversible structural damage. MicroCT technology has emerged as an important tool to evaluate root filling procedures, overcoming most of the limitations of previous studies. MicroCT enables visualization of the root canal filling as a 3D single object, or evaluation of cross-sectional images of the root at each level. The volume of the root canal filling occupied by the gutta-percha, cedar, and voids can be precisely calculated. Gutta-percha, cedar, and voids can be also depicted individually by coloring or made model transparent. However, complications can render micro-CT data problematic and quantitative use because of the high density of the root filling material. Scanning artifacts, such as beam hardening and partial volume effect, can obscure details of interest or cause the CT value of a single material or void to change in different parts of the image. These artifacts sometimes make it impossible to differentiate materials with similar densities. Although higher energy beams associated with the use of an attenuating filter can be beneficial, they are less sensitive to attenuation contrasts in materials and thus may not provide sufficient differentiation among the features of interest. For these reasons, it is important to perform different scans with alternative variables to determine the optimal parameters and material combinations before the experiment. Although root canal treatment has been shown to be a predictable procedure with a high degree of success, failure can also happen. Impaired healing is attributed to persistent intraradicular infection originating from non-instrumented canals or in the complex irregularities of the root canal system. Previously treated teeth with persistent infection might be preserved with non-surgical retreatment, which attempts to reestablish healthy periapical tissues by regaining access to the root canal system through removal of the original obturation, further cleaning and refilling. Therefore, the removal of as much filling material as possible is necessary to uncover remaining necrotic tissues or bacteria that might be responsible for persistent periapical inflammation and thus post-treatment disease. Most early laboratory-based studies used destructive and two-dimensional methods to determine the amount of filling material remaining after retreatment procedures. However, it is not possible to precisely calculate the volume of filling material remaining after retreatment using these methods. On the other hand, micro-CT approach allows for reconstruction and volumetric evaluation of remaining root canal filling materials after different retreatment protocols, overcoming the limitation of previous methodologies. The remaining filling materials can be expressed as a percentage of the initial root filling volume using this formula, where VB and VA mean the volume of the filling material before and after each retreatment stage, respectively. 3D models of teeth and filling materials can also be constructed for qualitative evaluation. Using micro-CT, it has been demonstrated that the use of supplementary procedures such as ultrasonic or laser irradiation during retreatment can improve the removal of filling residues from the root canal space. There are several applications of micro-CT in endodontics, which include marginal adaptation of filling and retrofilling materials, physical-chemical properties of endodontic materials, porosity characterization of root canal sealers, filling experimental internal resorptive cavities, stress distribution of nighttime instruments, cutting efficiency of nighttime instruments, development of 3D models for mechanical testing simulations using finite element analysis, production of 3D printed replicas of teeth to standardize sample for laboratory studies, calcium hydroxide removal from the root canal system, dentin removal during post-space preparation, adaptation of posts, pulpatosis in teeth of ancient populations, in vivo healing of periapical lesions after non-surgical or surgical root canal treatment in small animals. The importance of preclinical training has been well established in the literature for endodontic education. For decades, endodontic teaching has relied almost exclusively on the use of natural human teeth. Practice on extracted teeth is a universal method of teaching preclinical endodontics and gives students the opportunity to gain expertise before moving on to patients. However, cross-infection control associated with the manipulation of extracted teeth, along with ethical factors, are threatening this practice in some teaching institutions. These drawbacks have stimulated the development of alternative simulation methods for endodontic teaching. A transparent model tooth offers a convenient and useful method that can be used for studying and teaching about the morphology of teeth, as it provides a three-dimensional view of the root canal system. Additionally, they are standardized, easy to obtain in quantity, do not have any risk of infection, and can be a valuable aid for self-assessments. However, the hardness of the resin and the complex internal and external dental anatomy of the first transparent tooth models do not accurately reproduce natural teeth. The development of micro-CT-based training replicas produced using 3D printing technology have improved the use of artificial teeth for teaching purposes. Despite some limitations, these printing prototypes can be extremely valuable for anatomical teaching purposes. Additionally, replicas with different root canal complexities can be printed as oversized models, allowing the students to hold them in their hands and to observe details of the internal anatomy from different views. As imaging has been adopted in the modern dental education, the Internet has been used as an important educational tool. This was the main purpose for the creation of the web-based study guide called the Root Canal Anatomy Project by our group. This website has received extensive traffic since its development in 2011, with more than 1,100,000 page views. The high-resolution images and videos available for download at this website can be freely used for attributed non-commercial educational purposes by educators, scholars, students, and clinicians. One of the most interesting resources available to download at this website includes VXM files of all groups of teeth. A VXM file contains both the volume data and associated transfer function. This format can be used in the free volume handling app called CTVox from broker MicroCT. This app runs on either iOS or Android systems. CTVox displays a set of reconstructed slices as a realistic interactive 3D object with intuitive navigation and manipulation of both the object and the camera, a flexible clipping tool to produce cutaways views, background selection including custom scenery, and an iterative transfer function control to adjust colors and transparency. In other words, using a cell phone or tablet, it is possible to rotate, cut, color, highlight, shadow, or magnify areas of interest and more from real 3D datasets of different groups of teeth acquired by micro-CT technology. Considering that students nowadays are habituated to use web resources, digital and interactive 3D resources may increase the motivation of students to learn about the internal anatomy of the teeth. The purpose of this presentation was to demonstrate that, although the micro-CT method is not suitable for clinical use, in the last decade it has become a powerful tool for endodontic research as it offers a non-invasive, reproducible, an accurate technique for the qualitative and quantitative 3D assessment of the internal and external anatomy of teeth. Applications in experimental endodontology are now becoming extensive, as it can produce detailed information images of the root canal anatomy before, during, and after different endodontic procedures. A significant amount of information can be gleaned for the scans using dedicated software to extract morphological data from teeth, which would be otherwise impossible to acquire. Slices can also be recreated in any plan, while data can be presented in 2D or 3D images. Micro-CT digital data can allow for preclinical training and education regarding the fundamental procedures of endodontic treatment. Even though increasingly less time is devoted to teaching the internal anatomy of teeth in conventional curricula compared to the development of technical skills, nowadays students and clinicians may benefit from the sophistication of digital imaging technology. Given the constant progress in imaging technology, it is just a matter of time until the development of less costly high-resolution micro-CT system that required only a short learning curve. More information about this topic can be found on Chapter 7 of the book, Microcomputed Tomography in Medicine and Engineering, which was edited by Dr. Kan Ohan and will be published in 2019, and on the book Root Canal Anatomy in Permanent Dentition, which was launched in 2018. Finally, I would like to express my gratitude to Brucker MicroCT team for inviting me to this presentation, and you, of course, for watching. I hope you enjoyed. Thank you very much.
Thank you, Dr. Versiani, for your informative presentation. If you have a question you'd like to ask, please do so now. Just click on the Answer a Question box located on the far left of your screen. Questions that are not answered live today will be followed up by email in the coming days. Let's get started, Marco. Our first question. What are the advantages of using micro-CT approach compared to traditional methods for endodontic research?
Basically, we may say that micro-CT has three main advantages compared with the conventional methods. First, its non-destructive nature. It means that micro-CT allows that the same sample can be evaluated in different stages of the experimental procedures. But more than that, both external and internal aspects of the entire sample can be also analyzed simultaneously. Second, its accuracy. This is extremely important in research, as you can trust in the quantitative data acquired during the analysis. And finally, micro-CT allows to reconstruct digital cross-sections of the whole sample and stack them to create 3D volumes. Therefore, it allows the development of 3D images and videos of the sample, which can be used for illustrating the results of the research or even for educational purposes.
All right, thanks for that. We have a next one coming up. What are the main research areas in endodontics where micro-CT can be applied?
Well, nowadays, micro-CT technology has several applications in endodontics, as you could hear in my presentation. However, it is mostly used to describe the morphology of teeth and also to comprehend the effect of different techniques and materials used for root canal treatment and retreatment.
Thank you. What are the most important quantitative micro-CT parameters that can be measured in the study of root canal anatomy?
Evaluation of the morphometry of the root canal is important to understand how differences in the morphology of teeth can influence the root canal treatment in clinics. So root canals can be evaluated regarding 2D and 3D parameters, which includes area, perimeter, roundness, diameter, aspect ratio, volume, surface area, and its 3D geometry, such as structure model and unrod indexes.
Okay, thank you. Maybe one last question, Marco. Nowadays, how can micro-CT application be used for dental education?
This is a very important question because this is a new one, and there are a lot of potential in micro-CT because micro-CT is a non-destructive and high-resolution technology. It allows the possibility of learning tooth morphology by interactive study of surface rendered images and slices. In this way, micro-CT can contribute to the development of virtual reality techniques for endodontic teaching, transparent prototype replicas of teeth for preclinical training, websites dedicated to spread images and videos of root canal anatomy, such as the Root Canal Anatomy project, and the development of apps for cell phones or tablet like CityVox that can stimulate the self-exploration of the external and internal anatomy of the 3D model teeth for clinicians, students, and so on. That's it.
All right, great. Thank you again, Professor Versiani.
Thank you very much, Gil.
Thanks. Before we go, I would like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today will be addressed by the speaker via the contact information you provided at the time of registration. Additionally, if you missed participating in our survey, it will pop up again on your screen at the end of this presentation. Your feedback is important to us. Thanks for participating. We would like to thank again Professor Versiani for his time today and his important research. We would also like to thank LabRoots and our sponsor Bruker for underwriting today's educational webcast. This webcast can be viewed on demand through May 2019. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, goodbye.
Goodbye. Thank you very much for the opportunity, Kel and Bruker Marcus CT.